And today we will be converting everyone to the dark side. Just kidding. We're going over conversions though, as an introduction to dimensional analysis, i.e. converting something from one unit to a different unit, like inches to feet or feet to inches, that kind of stuff. By the end of this video, you should be able to use basic conversion principles and set up a dimensional analysis equation in order to convert pretty much anything you come across. First, why do you even need to know how to convert? Why is it important historically? And what are the patterns that we're going to use to set up dimensional analysis conversion problems? And then we'll go over how to deal with this thing every once in a while. These things are so many buttons. Oh my goodness, what do we even need to focus on this thing? And then how to set up one of those conversion problems to solve conversion math. There are many historical reasons why conversions are necessary, and getting the conversions correct, that is. But the one I'm going to talk about today is the Gimli glider, so story time. Basically, the story boils down to there was a flight that was going from Montreal to Ottawa to Edmonton in Canada, and they were using units of pounds per liter. So this flight was using pounds per liter in order to refuel it, so it could actually get from destination A to destination B and so on and so forth. It needs fuel to get there, and it needs a certain amount of fuel. These refueler people were calculating based off of pounds per liter. However, this specific plane needed to be calculated in terms of kilograms per liter. So that's a big difference. Overall, this plane needed about 20,000 kilos of fuel in order to make it from point A to point B. Instead, since they calculated based off of pounds per liter, they ended up with only about half of that, so around 9,000 kilos of fuel. Yike. So they ended up gliding 80 miles in the air just because they ran out of fuel due to a conversion error. Yikes. Can you imagine being one of those passengers on board, gliding to potentially your doom just because someone didn't calculate correctly using a conversion? Another fun conversion story is that one time we spent a lot of US tax dollars to send a satellite up into space, and they did a conversion calculation incorrectly. And so we watched that very, very expensive satellite, and we waited and we waited, and they built it, and we had all of these tax dollars fueled into the satellite, and we watched it with anticipation as it approached the target, and smash! It just kaboom, went into lots of pieces because of, yet again, a calculation error. So not only can these conversions be important in terms of saving people's lives on a flight, but also in terms of like saving your tax dollars to actually do something useful with the tax dollars instead of just watch the satellites smash into smithereens. If someone were to ask you to convert inches into feet or feet into inches, hopefully your grade school knowledge would kick in and you would go, wait a second, there are 12 inches in a foot, so you can kind of do a basic idea of how many inches would be in a certain amount of feet or vice versa. But how did you get that in the first place? Somebody had to have taught you at one point that there were 12 inches in 1 foot, that those two things were synonymous. That itself is a conversion factor. So the fact that there is 12 inches in 1 foot and 1 foot is equivalent to 12 inches is what we call a conversion factor. In other words, it's a number over another number with a certain unit. And the units in this case would be 12 inches over 1 foot or 1 foot over 12 inches. Those are your units. The inches and feet are the units, and you also have a number over another number in order to convert from one to the other. But you have two things that are equal to each other that you can flip-flop between the two depending on what unit you need. That's a conversion factor. Here are some very common conversion factors that you may or may not have seen. Some of which would include like that 12 inches, 1 foot, 5,280 feet per mile, 3 feet in 1 yard. Those are probably things you've seen often before. Less common would be like 454 grams in a pound. Those things aren't quite known off the cuff, but there's a few there for you to reference back to. Feel free to copy those down, take a screenshot, I don't know, whatever, to have an idea of what these conversion factors are when we use them and apply them in math and dimensional analysis. The ones that we will use more often in chemistry are metric prefixes. So those examples over there with milli, centi, kilo. I know that it says they're 1 over 1,000, 1 over 100, or 1,000 for kilo, but the way I like to use those metric prefixes is more in terms of 10 to the power of something. So in milli, we would say 10 to the power of -3, or centi 10 to the power of -2, kilo 10 to the power of 3. Those are just usually easier to work with when we deal with calculators and when we use the EE button, which we'll talk about later in this video. If you need some help remembering what symbols go with what measurement and what unit, take a look at this little chart here, and you'll see that we've got like millimeter is mm, centimeter cm, just to kind of jog your memory there. In chemistry, we use a lot of that mass, so grams, kilograms, not so much tons, but definitely grams we're dealing a lot with. So become very familiar with the fact that G does stand for grams. Another one we use a lot in chemistry is volume, for milliliter and liter. So become familiar with the fact that ml stands for milliliter and a big L, or capital L, stands for liter. So now that you know the importance of conversions and some basic conversion factors and what those are and their units, how do we set this all up to begin with? That's what we call dimensional analysis. But before we get to the whole mathy side, I just want to illustrate this with pictures. It makes more sense that way. So if you were going to play dominoes, and we have the dominoes set up as follows in this picture, how would we get that final product with the 5 dots on top and nothing on the bottom? What would you have to do with those first 2 dominoes there in order to get that product result? What would have to happen? What's the rule? Hopefully you're noticing right away that this one down here and this one up here would have to cancel out. So the fact that there is a 1 on top of one of the dominoes, and then there is a 1 dot on the bottom of the other domino, somehow means that we don't end up with anything here in the final product. So what we can say then from at least this setup, what the rule would be, is that if there's something the same on the top over here and something the same on the bottom over here, those two essentially cancel each other out. And then what we're left with is whatever was on top here in our final product, here. And then we also have whatever was left here in our final product on the bottom, because the 2 ones just go away, essentially. So using that same logic, I want you to pause the video here and determine what's the rule. How do we end up with 6 on top in our final product over here and nothing on the bottom? How did we get that with the 3 dominoes on the left-hand side? So hopefully you're using the same logic as before, and you'll see that anything that's the same on top with the same on bottom can cancel out. So in this case, our 4s here and here can cancel out. They're the same. Likewise, we have something else that's the same. We have 3 on top and a 3 on bottom over here. So we can cancel those out too. Now what we're left with is what we see in the product. We see a 6 on top, that matches, and we also see a blank space on the bottom. That also matches. Let's try another one. Go ahead and pause the video here and try and figure out what the rule is for this setup. How do we get a 1 on top and a 2 on bottom for the final domino? Which things have to cancel out? Think about it. This one's a little more tricky because the dominoes are not all right next to each other for you, but they don't have to be. The same rule still applies, even if a domino is far away from the other one. The idea is that if something's the same on the top and the same on the bottom, it can go away. We can get rid of it like yesterday's garbage. So let's try it. We have a 3 on top here, and that cancels with a 3 on bottom there. We have a 6 on top here, and we have a 6 on bottom there. Now this is that little tricky spot. We have a 5 on bottom here, and a 5 on top here. Notice that the dominoes didn't need to be right next to each other. They can still cancel out. What we're left with now is our 1 on top, which matches our product, and our 2 on the bottom, which also matches our product. So now if you're really understanding where that's going, go ahead and pause here and try and fix this. The idea is that we want to fix something on the left-hand side over here so that we get the product at the end, the 4 on top and the 1 on bottom. Go ahead and give it a try. Hopefully you saw right away that there's only one option for a 4 in these dominoes, and the 4 in our product needs to be on top. So what we would have to do is take this domino right here and flip it around. So we need to flip this guy over. And if we do that, we would have a domino that looks like this instead. Don't make fun of my drawing. It's pretty hard to draw on a Surface Pro, just saying, at least with my very limited skills therein. Now let's see if that fixes all of our problems. We see that there's a 1 here that can cancel and a 1 here that can cancel. Uh-oh. Now we're still stuck with 2 5s on the bottom and 2 6s on top. Doesn't quite fix our problem yet. So we still need to flip one of these dominoes in order for everything to work out the way we want it to. The question is, which one do we flip? If we were to flip this domino, that would fix our 5 problem. So let's give that a try first and see what happens. All right, so now we can cancel our 5s. Uh-oh, now we have another problem. Our 6s still don't cancel, and now we have a whole lot of 1s on the bottom too. We have to flip another one to make this work. Hopefully you see that we need to flip the last one in order to cancel our 6s. If we flip this one, that would kind of undo what we just did with the 5. So we don't want to flip that one. So let's flip that last one and see what happens. All right, now that the last one's flipped, our 6s can finally cancel. And what you notice that our other problem of there being too many 1s is now resolved in the fact that we can cancel this one with that one. Notice I didn't cancel all 3 1s just because there was 1 on top. There has to be 1 canceled per 1 on top and 1 on bottom. I can't just cancel the 2 1s on the bottom just because I have this one over here. I can only cancel 1 per 1, if that makes sense. So now we can see that our goal is attained. We have 4 here, which is our product, and we also have 1 on bottom here, which is in our product. Cool, we did it. Before we jump into some problems now with actual math, scary, let's figure out the basic setup that we're going to use for every single one of these problems forever and always. Don't cheat yourself on these steps. They really do help you get everything where it's supposed to be, and half the battle in math is just knowing how to set up everything. First step, draw a line, and then an equal sign and a space for your answer. In other words, you're literally just going to draw a line. Half the battle has begun. You have drawn a line. There is something on your blank paper. It's better than staring at nothing. You got this. We got a line, and now we're going to draw an equal sign because we're trying to solve something. So put an equal sign there. Now we also want a space for our answer. So draw another line. That's where we're going. We have a goal that we're going to, that we're trying to convert something to. Line, equal sign, line. Every single one of these math problems is going to give you something. It's their gift to you. Sometimes it's gift wrapped with a pretty bow on top and it's easy to determine what it is they gave you. Sometimes they bury it in a whole bunch of other convoluted nonsense that you don't actually need. Anyhow, every math problem is going to give you something. That given value with its units, i.e. kind of like 12 inches, 1 foot. So if they gave you 12 inches or anything like that, that's your given value. That's your gift. Put your gift as the first thing on top of your line. In other words, this is where you're going to put your pretty little bow gift wrapped value on top of the line, very first thing. That's your given value. See, it's a pretty little gift. Now, also in every problem, they're going to tell you what they want from you. They're going to say, hey, I want you to convert these 12 inches into feet. Okay, that's what they want you to do. They want you to get feet. That's the goal units, the goal ending point. So that's what we're going to put at the very, very end of our line after the equal sign and the space for our numerical answer. In other words, you've got your line, equal sign, line. Now you're going to put your goal units. So that's going to be like feet, inches, grams, pounds, kilos, whatever it is they want from you, whatever they're asking for, milliliters, liters, that's your goal, where you're going. You can't know where you're going to if you don't have a goal at the end of the line. I call this the magical line to freedom. We're going to follow and skip down this magical line to freedom to obtain a beautiful numerical number answer and that number answer is going to have clothes on. We need units for it. You wouldn't want to send your beautiful number you've worked so hard for naked out into the streets without any clothes shivering in the cold. Always make sure that your number has units with it, because units are half the battle. If you know your units, you can do any math problem, I promise you. Literally, it's just bookkeeping on units. And the last step is to add conversion factors until all of the units cancel except for the goal. I.e., this is the same thing we were doing with the dominoes. We could flip the dominoes, we could move the dominoes in any which way that we wanted until all of the dots on the dominoes canceled out and got us our goal, whatever the goal unit or goal domino at the end of the line was. That's what we're doing here, except with conversion factors, like the 12 inches over 1 foot. We have a bunch of those number units over number units as our dominoes, and we can flip them or move them along the line until we get the domino we want at the end of the line. That's the idea here. Do you know the way? This is the way. So I've given you my basic setup that I use for everything, literally everything. It doesn't matter if it's chemistry or not. Any conversion will work with this setup, and it's so much easier than so many other ways. Just work with me here. In the following format: our line, our magical line to freedom, our equal sign, our space for our answer, our goal units at the end, that's what they want us to obtain, what they're asking of us. The given value that they give us could be mass, volume, acres, feet, plottage, who knows, molecules. It could be anything. It could be anything that they give you, and then what they tell you they want for the goal. And then you're going to have to figure out these domino pieces that go in the middle in order for them to get to that goal. What if we started with 24 inches and we needed to know how many feet that was? Again, we would draw our line, our magical line to freedom. We'd put an equal sign and a space for our answer and the goal units. In this case, we have 24 inches that was given, the first thing on our line, and we need to know feet. That's our goal units at the end of the line after the equal sign. We also know that to go from inches to feet, we need a domino piece that has both inches and feet in it. In this case, 1 foot is equivalent to 12 inches, and I've put inches on the bottom so that it cancels with my given value of inches. What I end up with is 24 times 1, since those numbers are next to each other on top, but that ends up just being 24, divided by 12, because 12 is on the bottom, and that gives me 2 feet. If you have numbers that are all next to each other in the bottom, you need to multiply all the bottom ones, multiply all the top ones, then divide whatever's on top by whatever's on bottom. So I don't know about you, but I feel like when they first introduced these scientific calculators, there should have just been a class just on how to use these darn things, because there's so many buttons on here. Did you know that you can play games on this? I've never figured that out yet. Anyhow, in chemistry, we're going to be using the EE button a lot. What on earth is an EE button? The EE button essentially replaces the times 10 to the power of what? So instead of having to do a very large number or a very small number and having 10 raised to a caret and some value in parentheses and all that other jazz, we just use EE, and that replaces that whole gobbledygook, saves you time, and doesn't have as many calculation errors, because if you forget a parentheses, the calculator's not smart enough to know what you wanted it to calculate, and it calculates without the parenthesis and multiplies it by something else, and then you get a wrong number and you're really frustrated. So EE is the easy way to go here. So we're going to use EE because it's easy. In order to get EE to show up on your calculator screen, you need to first click the second button here, and then you also need to click the comma button, which has an EE above it, a very small EE. That's right here, and there's a little tiny EE right above that button. Now I know that mine is super worn down. You can't really see that's a comma anymore. This calculator has been well loved and has been through hell and back with me. So in case you can't see it too well on my calculator, check out on the screen. There's the second button I've outlined in a red box, and the EE or the comma button there. Second will make it so that it selects what's above the button. So it won't be a comma, it'll be the EE since you hit second. Kind of like a shift on your keyboard. In general, you should also know the difference between the subtract symbol and the minus symbol on your calculator. Those are two very different things. Anything that is over on this side is for calculating. So that's your subtract symbol, like minus, like 10 minus 7 is 3. That's your minus. However, your negative symbol, what says your like negative cash flow or like your negative in your bank account after the holidays, haha, rip bank account. That's your negative symbol for any kind of numerical value. In case you couldn't see it very well on my calculator, I'm also outlining it here on the calculator on the screen. So the physical minus sign to subtract one number from another is on the right-hand side of your calculator. And to say a value is negative or has a negative value, you use this bottom button here. Are you ready? Here we go. We're going to put it all to the test. If I walked 2.64 times 10 to the 6th feet, how many miles did I walk? Scary. When we read a question like that, your brain probably goes on the fritz. But I want you to remember our steps. Our steps are to draw a line. That's your first thing. Draw a line, put an equal sign, leave a space for your answer. Just like I have on the screen here. This is the way. I have a line, I have an equal sign, I have a space for my answer. The next thing I need to do is put my given on the first thing on the line and my goal at the end of the line. The thing that this problem gave me was the 2.64 times 10 to the 6th feet. So I'm going to put that on the top of my line, 2.64. Now I'm just going to put E because that's how I'm going to plug it into my calculator. E, 6, and this had units of feet. Don't forget the units here because that's how we know what goes on top and what goes on bottom for our conversion factors. So we've used our given. Now we need to know what the goal is. They want us to obtain miles. Let's put our goal units at the end. Because if we don't know where we're going, we don't know what to look for in the conversion factors. If you don't have units at the end, you don't know where you're going. Don't skip this step. It's crucial to solving math problems. The next thing we need to do is figure out what domino piece is going to get us from feet to miles. So if we look down at our conversion factors, those are our dominoes to choose from. We need to look for something that has feet and miles in it. In this case, hopefully you're seeing this one right here. That's our domino piece. There's 5,280 feet in 1 mile, or 1 mile has 5,280 feet. Remember, we have two different ways of making this domino piece. It could be 5,280 feet in 1 mile, or it could be 1 mile in 5,280 feet. Either way is correct, but we need our feet to cancel and we need miles to be at the end. So think of these again as our domino squares. We need a domino next to it that has feet in the bottom and miles on top. So we're going to choose this one in order to fulfill that destiny. If we go ahead and plug that in here, we have 1 mile on top, 5,280 feet on bottom. Then we can see right away that our feet cancel and we're left with miles, which is what our goal domino is asking of us. That's what we want. Finally, we just have to do the math part of this. We have one number times 1, which is just itself, 2.64 e to the 6, divided by 5,280. Let's plug that into our calculator using EE to get our answer. We've got 2.64, second button, comma, for the EE. Again, looks like this. 6, 2.64 E6, multiplied by 1. If you'd like to show that, you don't have to. It's going to be the same number anyways. Gives us that number, which is the same number, just not in the E format. Divided by, so the answer divided by, I just hit division right here. divided by 5280. And now I'm going to just hit the enter button. And that gives us 500. So our answer in this case would be, how many miles did I walk? I walked 500 miles. Ready to try another one? Let's give this one a go. If a baby elephant weighs 5.85 times 10 to the third pounds, how many tons is this? Same as always, we're going to start these by drawing a line. Pretty line. Then we're going to draw an equal sign and a space for our answer. We need to know what they gave us. They gave us the weight of a baby elephant, 5.85, and now I'm just going to again say E3 to replace this whole bit right there. E3 in pounds. Don't forget your units, and I draw that line just to separate the two, to separate our domino pieces from each other. And now I need to write what they want from us. What is it they're looking for us to calculate? They want us to calculate how many tons that is. That's going to go at the end of our line. And now we need to figure out our domino pieces conversion factors to get from pounds to tons. So if we look at our little box of conversion factors, hopefully you see that 1 ton is equivalent to 2,000 pounds. This can be written in two ways. We can have 2,000 pounds over 1 ton, or we can have 1 ton over 2,000 pounds. Those two things are equivalent, but we need it a certain way for our pounds here to cancel and give us tons in the end. So we need pounds to go on the bottom. We need that domino to go on the bottom. That means we need to use this one where pounds are on the bottom. So let's put 1 ton on top, 2,000 pounds on bottom, draw another line so we can separate it out. Here our pounds cancel, and we're left with 1 ton. That matches our end domino. Great. So now we just have to plug and chug in our calculator. In this case, we have 5.85 E3 times 1 here. Again, you don't have to show that if you don't want to. Anything times 1 is just itself. Divided by 2,000. Here I've plugged it into my calculator for you. That's what it should look like if you set it up correctly. And I'm going to just hit the enter button for our answer, 2.925 tons. So a baby elephant weighs 2.925 tons. All right, here's another fun one. If I, Dakanta, drove my dream car, a Stingray Corvette, dreamy, at 1.25 times 10 to the second miles per hour in a 135 kilometer per hour zone on the Swiss Autobahn, obviously not in the United States. Please don't arrest me if you happen to be a cop. Is she breaking the law? Am I breaking the law if I drive this fast on a Swiss Autobahn? Let's find out. As with any math problem that involves conversions, we're always going to start with the same thing. We're going to draw our magical line to freedom, an equal sign, and a space for our answer. This is the way. In this case, the question is indirectly asking you for a conversion to kilometers per hour. So let's start with what they gave us. That 1.25 times 10 to the second miles per hour should be our gift. That's going to go on top. Notice that I have written 1.25 E2 miles over hour. That's miles per hour. The number is always going to be stuck to or velcroed to the first unit that it comes in contact with. Now the thing they're asking us for is kilometers per hour. So that should be our goal units. We'll put kilometers per hour at the end of our line. At this point, we want to do some critical thinking and notice that our hour already matches. We don't need to be concerned with our hour. The only thing we need to convert here is our miles to kilometers. So we need to figure out how many kilometers are in a mile, how many miles are in a kilometer. That's our domino that's missing here. So if we look down to our conversion factor table, we'll see that 1 mile is equivalent to 1.609 kilometers. Again, this can be written as 1 mile over 1.609 kilometers, or 1.609 kilometers over 1 mile. In this case, we need kilometers on top so that it matches our answer, and we need miles on the bottom so that we can cancel this miles here. So we have to use this setup for our domino in that spot. 1.609 km, kilometers, over 1 mile. Now my miles cancel here and here, and I am indeed left with kilometers for my final answer on top, and hour for my final answer on bottom. Here, we only have ones on the bottom, so 1 times 1, 1 there is just 1. Don't really have to do anything there. And on top, we have 1.25 E2 times 1.609. So when you plug it in your calculator, it should look like this. Let's hit that enter button and figure out our answer. So our answer is 201.125 kilometers per hour. So 201.125 kilometers per hour is what I would be driving my dream car in. Now the speed limit is 135 kilometers per hour. Am I breaking the law? Heck yeah, I am. And to summarize this video for today, let's just review the steps for dimensional analysis. Setting up any conversion ever in the whole wide world will get you there using these steps. First and foremost, draw that magical line to freedom. Just draw a line. This is the way. It's a lot less intimidating to have a line on the page than just a blank page staring back at you, especially if you're unsure of yourself working with math like I am. Number 2. Put what you're given, your gift. Put that as the first thing on the top of your line, all the way to the left. Then the question asks you what it wants. Put those desired units after the equal sign at the end. It's the goal, so you know where you're going. You always have to go towards the goal. By the way, the goal units will always go on top. That's a good way to remember it. So goal units go on top when you're looking at your conversion factors. And finally, get all the units to cancel until you have attained your goal units. So play with those dominoes. They can be flipped one way or the other. Those are your conversion factors that you have to look back at your conversion table for. And you can flip those one way or the other, feet over inches, inches over feet, grams over kilograms, vice versa, until you get all of the dominoes to cancel and you end up with the goals that you want. If this video was helpful for you, please go ahead and hit that like button, that thumbs up, and subscribe to my channel if you haven't already. Hope your day is just ducky and that your calculations are everything they're quacked up to be.
No ducks, no glory.